Hello, everybody. The topic of my presentation today is application of FactSage in steel making. At first, I want to present short our institute. Our institute is oldest one in steel making. The institute is more as 150 years old. It was founded in 1874. And our first director, first professor was Professor Ladle. All of you know the phase or structure Ladleburite. We are small institute. How I can change it? No. Yeah. Okay. Good. We are a small institute. We are in east part of Germany, near to Poland, near to Czech Republic. We have only one professor at my institute, only me, and we have now 21 researchers by 15 PhD students. I have good PhD students, and so in year 2025, my 15 PhD students published 47 Scopus publications. In which area? In 2025, 4 papers was about hydrogen reduction of different iron ores, 11 about thermophysical properties of liquid slags or liquid metals, about steel powders, it was 4 publications, steel design 6, and 7 about slag reduction. Here you can see my team. I am here with our metallurgical kettle, and it is my researchers. Today with me is Anhelina Mospan. She will present short one model from which he was developed. And typical we have our funding is about 2 million euro per year, and typical we have at our institute more DFG, Deutsche Forschungsgemeinschaft projects, but some projects from European Union too. Okay, we are not developers of FactSage. We are not developers of database. We are only users. And we use FactSage every time in our research, in doctor thesis work, in projects, or in diploma works. And I want to present only short results or some examples of our calculations. The first example is about cooling factors. Cooling factors of different alloying elements. The knowledge is very important for level 2 by steel plant, for static model of BOF or EIF, for temperature control model in secondary metallurgy. In the literature, you can find different values of cooling factors. It is depend on steel plants. In some steel plants, the cooling factor will be used with unit Kelvin per 1 ton of crude steel, and can be Kelvin per charge mass, can be Kelvin per 10 kilogram per 1 ton. Yes, it is very, very different. It's depend of steel plant. Yes, it is not homogeneous. Here is one example from Deutsche Edelstahlwerke from Siegen, and you see in Siegen the people use unit in 10 kilogram per 1 ton of crude steel. During one diploma work, the different cooling factors will be calculated by us at institute using equilibrium. By under condition the H is 0, and the student calculated cooling factors as function of temperature, chemical composition of alloying element and as function of steel melt state. Yes, because we can have killed steel, we can have not killed steel, or we can have different temperature, or in this case you see it is in BOF with different carbon content. It is by 50% of blowing oxygen, it is near to end of blowing oxygen. And you see the cooling factors change with condition. After them, the calculated cooling factors were implemented in one integrated steel plant, in static model of one integrated steel plant. And after implementation, the standard deviation, the standard error of static BOF model is now less as 18%. It's very good, yeah. Okay. The next example, it is about liquidus temperature. We need knowledge about liquidus temperature for setting of casting temperature in mold or in tundish of continuous caster, for setting of tapping temperature on BOF or on EIF. At our institute, we can measure liquidus temperature in one furnace using the steel samples about 200 gram. I want to show only one example for the steel alloyed with chromium, nickel, aluminum. Yes, the steel has 5% of aluminum, and measured temperature was, I have problem with sim, but it's okay, 1494. And after them, okay, I must stay here, yes? After them, we calculate the liquidus temperature with FactSage, with database FactPS and FTMX. The calculated temperature was 1453, but in case of F steel, it is lower. So we checked in this case us with thermocalc, and with thermocalc we calculated 1453. So you can see that both two calculated and measured temperature are in good agreement. Next example is about evaluation of silicon holders. We used silicon in steel making in BOF process as slag former or as for heat in BOF, and our task was to calculate how many the silicon 63 must be used to replace 1 ton of silicon 75. Typical on BOF we use in Europe, in Germany, phase with 75%, but sometimes we have secondary silicon holder, recycled silicon holder. And condition, the calculation was done under condition, the basicity. Under basicity, we understand the ratio between calcium oxide and silicon oxide must stay 3.5. And iron oxide, we used iron oxide in the slag to dissolve lime. And in this case, it is metallic iron. The metallic iron content in the slag must stay 17 mass %. In this case, one student used equilibrium module and reaction module, and you can see the results are the same. Next example, phosphorus distribution or phosphorus partition. We can measure it by us at Institute as function of temperature, as function of chemical composition of the slag or of the steel. And we can measure it in two directions by phosphorus transport from the steel to the slag, and again from the slag to the steel. Here you can see comparison between phosphorus partitioning, and you see the value are the same. Good. After them, we analyzed 25 industrial heats. We analyzed phosphorus distribution from this steel as function of basicity, as function of tapping temperature. 25,000 heats are from one steel plane, which works with tapping temperature between 1,600 degree and 1,600 degree 50, and with low basicity, with basicity about 2. After them, we compare us with HKM from Duisburg, and HKM in Germany works typical by higher tapping temperature. You see here, it is HKM, and by higher basicity, yes? So we match the data from 2 different steel planes, and you see they are in agreement. After them, now it's not good story, after them we calculate phosphorus distribution with FactSage. We're taking again 25,000 heats. Yes, it was with one macro. Typical calculated phosphorus partition must be higher as industrial. And in some case it is so. For example, here, here it is higher. But you see, we have region where calculated with FactSage phosphorus distribution is lower as industrial. My opinion, it is doing by few data for oxide system with phosphorus oxides. I look at by you at few sites. It is only what we have now, but FactSage, so we cannot calculate all condition in steel plane, in BOF, with these data. Good. Next example is about hydrogen solubility. It is one famous diagram from Professor Larry Holapa from Finland, and we calculate this diagram with FactSage. And you see, they are the same, yes, it's beautiful. And the dissolved hydrogen in calculated dissolved hydrogen in pure iron is about 24.526 ppm. And in year 1974, Bosstein measured 88, sorry. The same, yes, it's good. Now we are by analyzing of industrial heat. We have now 12,000 industrial heat for hydrogen measurement. And it is first results independent of sulfur, and you see the hydrogen solubility decreases with sulfur in steel melt. I think I have a lot of examples, or I have time or not? Oh, okay, good. The next is about thermophysical properties. Yes, we can measure at our institute viscosity, surface tension, density, crystallization temperature, flow behavior, and heat conductivity of molten steels, metals, and of molten slags. It is some examples. Blast furnace slag. B0 is from Germany, what we now have. We use in Germany iron ore from Brazil, Sweden, from Canada, and so in our slag in Germany today, in BF slag we have 10% of alumina oxide and titanium oxide less as 1 mass percent. If we will have in the future iron ore, for example, from Australia, we will have more alumina oxide in our slag. And BF slag is very important because BF slag is now used to 100% in cement industry. And the knowledge of thermophysical properties is very important for granulation process of BF slags. Okay, so we measured viscosity as function of temperature of alumina oxide, titanium oxide. The viscosity increases with alumina and decreases with titanium oxide, but we have breaking points, yes? Breaking points on our viscosity lines. And the breaking points, for example, in this case, you can see it, breaking points at first decreases with titanium oxide and after them increases again, yes? And to explain it, we calculated solid fraction and formation temperature of solid fraction in our slag, in our different BF slag, by cooling, compare with our breaking point, and what we can see, our breaking point correlate perfectly with formation temperature of milliliter and perovskite. BOF slag, it is few data in the literature about BOF slag because it is not easy to measure it. BOF slag slags react every time with crucible material. Our task was here to investigate influence of magnesia oxide on viscosity of BOF slag. We have in Germany some steel plants which work with 2% of MgO, some with 8, for example, by ThyssenKrupp Ox 1 work every time with 8, and Ox 2, one company, but two different steel plants with 2. Okay, what we can see here, it is our measurement, comparison with the literature, and after them, we calculate viscosity with different models from literature and with FactSage. In this case, it was old FactSage version 7.2. And what can we see? In liquid determined ratio, the calculated viscosity is near to measured. But after breaking point, yes, it's not good. So, in the next project, our task was to analyze viscosity of EAF slag. Our task was to increase liquid determined ratio, and we made it with aluminum oxide. So you can see here viscosity of EAF slags from Germany again, from one steel plant after production of construction steel, and in the slag after production of construction steel, we have every time a lot of iron oxide. It is depend on quality of the scrap. If we have very bad scrap, we can have 50% of iron oxide in our slag. Okay, so we have experience that after solidification, the model in FactSage works not very well. So we calculated with FactSage, we measured viscosity. After them, we calculated FactSage of EAF slag in liquid state, yes, in pure liquid state. After them, we calculate solid fraction by cooling. And we calculated with FactSage viscosity of liquid slag and solid fraction in Einstein-Roscoe model. And now we have very good agreement between calculated and measured one. Okay, the next example, ladle slag. It is for a refractory company, but not for RHI, it was for other one. And here our task was to investigate the infiltration of ladle slag in refractory materials. So we had two slag, one slag with 1% of silicon oxide and the next one with 20% of silicon oxide. With silicon oxide, viscosity of ladle slag increases, yes, and viscosity increases, we check it with experiment. So you see 1% of silicon, our slag is in refractory. And by 20% of silicon, our slag is on the surface of refractory. It is other refractory, yes, it is ladle refractory for slag region. And in this case, we calculated interaction between infiltrated slag and refractory. And we found that by 20% of silicon, we have spinel formation. Yes, if slag is in the refractory, they interacted with refractory, and we can found spinel. So we made experiments. We taken the samples and we look on the sample in SEM, and we found this new layer, the new spinel layer. Yes, it was mapping from SM, and so if we have new layer, new spinel layer in refractory, the infiltration, the further infiltration of slag is stopped. Yes, okay, it was my part, and now is Anhelina.
So, hello everyone, my name is Anhelina and I'm PhD student of Institute of Iron and Steel Technology, and today I would like to give a short insight into our work. So, I simulate metallurgical processes in FactSage, and sometimes I simulate it looking busy too. So, but the main idea of my presentation is to show that FactSage can be used not only for single equilibrium calculation, but also for repeated and automated process operated simulation. So, and in this work, FactSage is combined with Excel and macro processing. I used FactSage macro processing to build step-by-step process model, and the model connects Excel, FactSage equilibrium file, stream saving, and automatic output reading. The input data were prepared in Excel. The model contains also the stream, and in FactSage I prepared separate equilib files for the relevant phases. And the macro script controls. Oh God! Just a moment. It's okay. So the macro script control whole calculation. First, it reads the input data in the Excel. Then it opens the prepared equilib files. Then it sets the reactant masses and temperature. After that, it starts the equilibrium calculation, and then it saves the new equilibrium products at stream. And finally, it writes the calculated values back to Excel, and this procedure is repeated for each time step. So, and the focus is not only the thermodynamic results, but also on the workflow, FactSage workflow. Excel input, FactSage equilibrium, macro processing, and automatic output processing. And today I will show 3 examples. Firstly, I will show a desulfurisation simulation of hot metal. Then I will show the interaction between magnesium oxide carbon refractory and ladle slag. And at third, I will show the part of blaze oxygen furnace process simulation where FactSage macro processing was used to follow temperature and composition change step by step. So, go to the first example. In the first example, I simulated the desulfurization of hot metal by basic slag, and the calculation was done with FactSage equilibrium and controlled by macro processing. After each equilibrium calculation, the sulfur content in metal and sulfur content in slag were written back to Excel automatically. So, and on this graph, on this slide, this graph will not write manually. So, it is the output of a repeated FactSage macro calculation. And for this thermodynamic calculation, I used 3 databases: FT-MISC for liquid iron-based metal phase, also FT oxide for slag and oxide silicate phases, and FactPS for pure compounds and possible gas. And this model is pseudo-kinetic equilibrium zone approach. That means that only part of slag and only one part of the metal react in each time step. And in this example, 20% of metal and 30% of liquid slag were allowed to react in each time step. But after the equilibrium calculation, the reacted part was mixed back with the remaining material. And the results shows the clear sulfur transfer. The sulfur content of liquid metal decreases from 0.3 weight percent to 0.003 weight percent. The second example is about a refractory during heating. Here I simulated the phase evolution of two refractory composition during heating, and the calculation was performed in FactSage 8.1, and the calculated was performed from 1000 to 1700 degrees Celsius. The pressure was 1 atmosphere, the atmosphere was inert. I also used 3 databases, FactPS, F2Oxide, and FTMISC. And the main result is both materials remain mainly magnesium oxide and graphite. The basic of our material structure is stable during heating. Then in the next step, I simulated the interaction between refractory material, refractory and ladle slag. And the same slag composition was used for both calculation. Here again, the advantages of macro workflow is very important. The same calculation structure can be used for different material cases with different chemical composition. I only change the input composition in Excel, and the macro can repeat the calculation and write the output values to Excel. And on this graph, I selected magnesium oxide in slag as a main output. This is a useful parameter because magnesium oxide is the main component of refractory, and so if magnesium oxide in slag increases, it means that material from refractory side enters the liquid slag. And the important point of this slide is the same FactSage macro workflow can be reused for different refractory systems. And the third part of the presentation is about place oxygen furnace simulation. This is example where macro processing is most important. Here I used FactSage macro processing to build a step-by-step process model. The model is not only single calculation, it is a loop of many equilibrium calculation. And this is why macro processing is a central part of this model. Without the macro, every step would have to be done manually. And with macro, the process becomes automatically. And so the output includes temperature, chemical composition. The calculation basis was 50 minutes process, 1 minute time step under adiabatic conditions and 1 atmosphere. This slide shows the temperature evolution calculated by FactSage simulation. The temperature was not prescribed after each step. It was calculated by FactSage from the equilibrium state, and the calculation was under adiabatic conditions, and these graphs shows two curves. The temperature of liquid slag and the temperature of the liquid metal. The hot metal temperature increases during the whole process, and the slag temperature behaves a little differently. At the beginning, it first decreases or stay lower, and for me, the important results is not only the absolute temperature. The important point is that FactSage macro processing can follow the thermal response of the blaze oxygen furnace step by step. So, and the model follows not only composition changes, but also temperature changes. This slide shows the transfer during process. Here I selected carbon, silicon oxide, and gas phases. So the carbon in the liquid metal decreases strongly. It goes from about 4 tons to almost 0. So, and this represents decarbonization during oxygen blowing. And the carbon is oxidized and transferred mainly on gas phases as CO or CO2. Silicon in liquid slag is decreases. At the same time, silicon oxide in in metal decreases, in slag increases. So, and on the one hand, elements disappear from liquid metal. On the other hand, products appear in slag and gas phases. So, and this is the main advantage of FactSage workflow. It does not only give one final result, it follows how the system changes with time. So, and in all our cases, in all our presentations, the main tools was FactSage, and general message from my part that FactSage can be used not only for single equilibrium calculation, but also for repeated calculation. So thank you very much for your attention, and Glück auf!